Let us start with one very important thing. So far we have been dealing with fluids at rest, fluid statics. Okay. Now the question is, what happens when fluids are moving? So let us first start with a very simple idea. What is pressure? Force per unit area. Now, if I look at statics, it doesn't matter, you know that in static situation, that a liquid will actually exert pressure in all directions, right? So, if I had an object that was at rest, and you look at this point, the pressure acts equally in all directions. So, this we call Pascal's law, okay, one of the Pascal's laws. Now, let us think about a piece of paper like this, and if I blow air at this paper, which way will it go? That way. So, can I say pressure in this case is in that direction? Right? But what is very interesting is if I took two pieces of paper, now you know that air molecules are going to come. In fact, we can just do it very easily, and the basic understanding is that if you take air molecules coming and hitting this way and air molecules coming and hitting that way, okay, this is not liquid, but the basic idea will translate to liquids as well. Okay. If I now remove the air molecules here, not remove, but reduce the number of air molecules here, you know that the pressure in this direction will reduce, and in that direction you will have more force than this side. Now, one way to do that is to just simply blow away the air molecules by pushing my hand. You may not believe it will work. It won't work for too long because immediately air will rush back. But you can notice it for a very short time. Okay, 1, 2, 3. So you can see that I didn't touch it. As soon as I do that, there is lower pressure here, and so this one starts to move. But what is interesting is here at least I am using my hand and removing air. If I blow away the air here, which means I am actually giving a large wind in this direction, or like kind of I'm moving air in this direction, and when air moves in bulk we call it wind. Okay, so basically let us say that I am moving air in bulk here. What is going to happen? Well, air molecules will come back, but if suppose I said 1, 2, 3, 4, just imagine that there were 4 air molecules here in this space. Obviously there will be millions, but just to make it easier, 1, 2, 3, 4. By pushing it, I have not made this 0, but one molecule is here, the second one is there, third one is there. That means on this area of the paper, or this width of the paper, you have 2 instead of 4. Which means obviously the way they will go and hit this will become lesser. So let us try the same thing. If I blow it here, you expect that this will move that way. And as soon as it crosses this side, now I am blowing on that side, so it comes back. You can see that, right? And you can see the same if I actually use 2 pieces of paper. So if I try to take, let's say, this one and this one. Okay, well, it's everything written on it, doesn't matter. Okay, so if I take 2 pieces of paper and I blow in between, right now air molecules are going back and forth, and air molecules are going on that side and on this side, hitting from all directions, right? What if I blow away the molecules in between? They should stick together. So this says something quite interesting. It says that if I blow air in this direction, the pressure in this direction reduces. But if I blow air in this direction, well, if this is low pressure, it should come this way, right? It doesn't come. You understand my question? I just told you that this is lower pressure. But if it is lower pressure, this is how this goes that way. But if I am blowing like this also, it's low pressure. Then it should come this way. So, and so what? Correct. So there are 2 kinds of pressures that we must think about. This is static pressure. When you talk about F divided by A, or thrust divided by A, now static pressure is very different from that. Well, that's also thrust by area, but in this case, one, you know of course that it is equal in all directions. Just imagine the situation. Because there are air molecules rushing randomly in all directions, there is a push this way, there is a push that way, that way, that way, that way. But because there is a wind in this direction, you can see if I try to do the same by, in fact, let me do it like this so you can see. Okay, I am going to blow this one. You will see that this fellow is going to come towards you, that will move in that direction, and this fellow is going to go away. So it does two things. Let's see. Okay, so that means on this, actually the net force is this way, but on that the net force is that way. So apart from pressure, there must be something else. Apart from static pressure, what we should be able to call dynamic pressure, or because there is velocity for air. So clearly, when air has velocity or liquids have velocity, you can't treat them exactly like you treat the static case. But when liquids have velocity, apart from doing something in this direction, they also do something in this direction. In fact, they seem to be doing opposite things. In this direction, you have a large velocity, but in this direction, actually, it's lower pressure. So it's not actually pushing as it used to. Now, what I'm going to do is very general. You can't obviously use it for problem solving. And please remember, liquids, we are going to treat them as incompressible. This is just to get an idea. Why is the liquid, in fact with air it is easy, why is air exerting pressure on that wall or this wall? Because it's going back and forth. Why is it exerting pressure on this wall? Because it's going this way and back, right? So it goes and bombards, and that basically causes pressure. Now it bombards equally in all directions, so it causes pressure equally in all directions. This is static air. Now if I decide to blow air, what is going to happen is basically as this has to move out, imagine that the distance has now increased. It has got spread out like that. Now if you took this area earlier, maybe there are 5-6 molecules which went and bombarded. Now what is going to happen? There will still be some molecules that will go and bombard, but much less. So therefore this direction the pressure has decreased. So when speed increases, we say that pressure in this direction decreases. Now we don't usually say direction, we just say pressure decreases. Because then when we talk about pressure of a fluid, a gas or a liquid, generally we mean static pressure. But this is moving, correct, it's moving like this, but this pressure is just like static pressure. Is that first idea understood? Clear? Okay. Now, but with liquids you can't even say the molecular distance has increased. What can you say instead? If liquids are moving very fast, what can you say? So, if I had water moving very quickly, obviously its density does not change because you talk about water as incompressible, but you already know that the pressure is because the molecules are pushing each other. Now if something is moving very rapidly, this fellow and this fellow might have been at this intermolecular distance. If it was slow, that means they are pushing each other quite a lot. Now when you make it move quite rapidly, what is going to happen is this will basically move a little further. So this diagram will look like this, and don't quote me on this, okay, because it's obviously not true. But I want you to just imagine it like this. Still rushing through. So now because of this, what has happened? Overall intermolecular distance has increased. So pressure that way, this way, every way, pressure has decreased. But if I kept something here, apart from the fact that the intermolecular forces, which is the cause of static pressure, has decreased, there is also going to be a bombardment and a momentum change. Now that was not there earlier, now there is, because it has a velocity. So that means it will exert forces which probably are larger than just ordinary static pressure, but you must split this up into two pieces. The force exerted by the liquid will have two parts. One, momentum change force, we can call that dynamic pressure. Dynamic because it's moving, because of its movement, because of its velocity change, because of momentum change, there is a force. That force divided by area is pressure. Do you think this is going to act equally in this direction? Or do you think it's only going to act in this direction? It's going to act only in the direction of the flow. Dynamic pressure is not going to act in all directions equally. But static pressure, that is going to act equally in all directions, because static pressure is the result of intermolecular forces. Right? So this is the cause of static pressure. This guy pushing that fellow pushing this one, and so on. The distance has increased a little bit. Now the distance increase, what I have shown is completely wrong. Well, if this happened, the liquid's density is going to change dramatically. What I have shown for air is reasonably correct. Okay, but for liquids, this is completely wrong. So this fellow will look like this fellow almost. But at the atomic level, a small change in distance, you've already seen that graph, small change in distance can mean large change in force. It is not as bad as in surface tension. In surface tension, a push became a pull. Here, a big push became a slightly smaller push. It's not really bad. But you know that it can become even a pull, right? So can it become a slightly smaller push? Absolutely, no problem. Okay, but the density hardly changes, because the distance it changes by is very, very small. So is the broad principle correct? Now this guy called Bernoulli tried to understand the difference between these two types of pressures. Pascal spent a lot of time on static pressure, and Bernoulli basically tried to figure out rules of how fluids or particularly liquids behave when they are moving. Turned out he came up with some very interesting discoveries, and one of the things that he discovered turns out to be the same as energy conservation. Okay, so today we are going to learn Bernoulli's principle through energy conservation, or Bernoulli's equation through energy conservation. Very simple equation, very simple statement that you usually make of Bernoulli's principle is to say, when a fluid flows rapidly, these molecular distances will increase, so the static pressure will decrease. Now usually people don't say static pressure, they just say pressure of the fluid decreases. But then there's a problem, because if you say pressure of the fluid decreases, well, if it decreases, it should come this way. Why does it go that way? The pressure of the fluid decreases means static pressure decreases. You can see that with air, you can see that with water. Okay. And many times you will see experiments where the people show you what happens when you reduce static pressure. Maybe we'll do an experiment. Shall we? Apart from this, let's try one more experiment.